Let's do a quick example of another calculation using the normal distribution and z-table. So here we go. The scores on a national achievement test are normally distributed with a mean of 540 and a standard deviation of 110. So let's say you scored 680. What proportion of students scored lower than you but higher than the mean? So between your score, 680, and the mean score, 540. And then part B, what is the 97th percentile score? So this is some terminology you should know. The 97th percentile, that's the value which 97% of the time the random variable takes a value lower than. So that's a very good score, right? 97th percentile score. So that means 97% of students who write this test will score below that. Only 3% above. All right. So here we go. Part A. You scored 680. What proportion of students scored lower than you but higher than the mean? So the key point here is to realize, okay, we can do all this stuff because we know the distribution of scores. It's a normal distribution, and we know the parameters, the mean, and the standard deviation. So in this question, both part A and B, we're working with this normally distributed random variable with a mean of 540 and a standard deviation of 110. And so, in part A, we're looking for if you scored 680, what proportion of students scored lower than you but higher than the mean? So we want to know the probability that this random variable is between the mean, 540, and the score of 680, okay? So we're looking for this probability right here. Now remember, the way we can do this is because we're dealing with a normally distributed random variable, what we're going to do is take these two values and standardize them, turn them into z-scores, and then we're going to use the z-table to finish this off. So here we go. So we got two different z-scores, one for 540 and one for 680. Let's call the first one z1. So to do that, we're going to take our 540, subtract the mean, which is 540, right? The mean score is 540. And divide by the standard deviation, 110. And of course, you're going to get 0 divided by 110, which is going to be 0. And then I'm also going to turn the 680 into a z-score, 680 minus the mean, 540, divided by the standard deviation, 110, which is, what's that? 140 over 110, which is 140 divided by 110, 1.27 of it. Okay. And now when you're using the z-table, none of your answers are going to be exact anyway, so I generally keep just 2 decimal places. There's sort of no point in going any further because typically z-tables are only going to be accurate up to 2 decimal places anyway. So we turn these two values into z-scores. So now the probability that a random variable x, which represents a score of a randomly selected student on this test, is between 0 and 680, that's the same thing as the probability the standard normal random variable z is between these two values. So 0 is less than or equal to capital Z is less than or equal to 1.27. And now that we have a probability involving z, we can use the z-table to figure it out. So every time you do one of these, I want you to draw this picture. So draw a picture. Doesn't have to be very accurate, of the standard normal distribution. So this is a normal distribution with mean 0 and standard deviation 1. So the 1 standard deviation away. Remember that that happens at the inflection points here to get sort of a rough picture. And I want to shade this area between 0 and 1.27. So the area I'm looking for is this right here. Between 0 And in here I have my 1.27. And the reason, let's just make this a little bit cleaner. The reason this is important to do is because these z-scores, when you're doing a problem like this, the z-score is kind of a halfway point between the values of your random variable, the actual scores on the test, and the probability. And so people kind of get messed up sometimes with it. They don't really know what a z-score is. It's just some part of some process which gets you the answer to a question about a normal distribution. But it's important to remind yourself that these values 0 and 1.27, they're values of the random variable z. They go on this axis, which is labeled little z. Probabilities are areas. Z-scores are values of a random variable. Okay? People can get confused here because, like I said, the z-score is kind of in between the probability, the area that you're looking for, and the values that represent scores on tests. So remember, these also represent scores on tests, 0 and 1.27. We just took this normal random variable, and when we turned everything into z-scores, we just shifted it and scaled it so that its mean is 0 and its standard deviation is 1, so that we can use the z-table. Okay, so I want this little area here, and now I just need to match this up with this z-table. If you're using a physical piece of paper z-table, what you'll have to do is take the area on the left of 1.27 and subtract the area on the left of 0. But if you use the interactive z-table that I usually use for these kind of problems, where you just drag these points on the axis around, you can just match it up. So I'll drag the points on the axis around until I end up with 0 and 1.27, and it will tell me the area there is 0.3980, or 39.8%. So therefore, if you scored 680, that means 39.8% of students who take this test will score lower than what you scored, but higher than the mean. So it's a pretty good score. Very good score. Okay, great. Now the next part. What is the 97th percentile score? All right. So the 97th percentile is the test score. So I'm looking for a value of x, which is going to correspond to a value of z when I standardize on this axis, where 97% of the area is on the left. So what I'm going to do is I'm going to use the z-table to figure out the z-score that has 97% area on its left, and then I'm going to use the z-score formula backwards to turn that into a test score, a value of the random variable x. Oops. So here we go. So to get the 97th percentile score, let's draw this distribution again. I'm sort of going backwards, right? From the way I did the last problem. I'm starting with a probability, and what I want to get eventually is a value of x, my random variable, which represents a test score. Okay, so I'm looking for the value right here. Maybe I'll call it z star since I don't know what it is yet. Where this area in there, the area on its left, so I'm not including little piece in here, I'm including everything on the left of z star. So this area in here I want to be 0.97, okay? So what's the z star that gives me an area of 0.97? Well, I'm looking for the probability z is less than or equal to z star, right? That's what this picture is saying. Z star is the z-score where the probability of taking that the standard normal random variable takes a value smaller than it is 97%. And again, now I just consult the z-table. If I have a paper z-table, I'm looking up 0.97 inside the z-table in the section that gives me areas on the left. Usually that section will have 4 decimal places, so I'll actually be looking up 0.9700. If you're using the interactive z-table, then again, I'm just going to drag things around, and I want to drag one of the dots on the axis all the way to the left to make my area go to infinity, and sort of click to keep it there. And then I want to drag the other one around until this number that represents the area on the left is 0.97, as close as I can get. It takes a bit of fiddling. Okay, so after a bit of fiddling, what I got is that the closest I could get to 0.97 is 0.9699, which is very close. And then my z star came out to be 1.88. So that means that, yeah, if I take this to be 1.88, the area on the left is 0.9699, which is as close as I can get with this z table to 0.97. So there you go. There is my 97th percentile in the for the standard normal random variable. So that's the value of the standard normal random variable z that has an area of 97% on its left. So to finish the question, all I have to do is turn this, which is right now a z-score, I have to turn this number back into a value of my random variable x. And all I have to do is use the z-score formula. So the z-score formula, z equals, oops, so that's a little z, little x, minus the mean, divided by the standard deviation. Right? That's the z-score formula. And so now this time, instead of knowing these three, I know these three. This one, this one, and this one. So I'm going to use, for my z-score, 1.88. X, the thing I'm looking for. Mu, the mean on the test, it was 540, right? Double check that. Yes, it was 540, and the standard deviation is 110. So I divide by 110. All right, and after a bit of manipulation, you should come up with x equals this times this, move that over, 540 plus 110 times 1.88. Okay, so let's do that real quick. Sorry, 540 plus 110 times 1.88. All right, and so I got 746.8. Great. And just, in the context of this question, this is supposed to represent a z-score, sorry, a test score, which I'm assuming is a whole number, maybe not, but from the context it looks like it. So really, to answer the question, I would go up to the next whole number. So I should say, if you score above the interpretation of this 747, then 97% of students will have scores below yours. Great. Cool. And one more thing I want to mention is that, a thing to be careful about is that all of this stuff we did, both in part A and part B, it was possible because all of this calculation was possible because of this. Because we got to assume that we were told that the scores are normally distributed. If you take any random variable, normally distributed or not, any kind of distribution, you can run its values through the z-score formula. And what does that do? That gives you a new random variable whose distribution is a shifted and scaled version of the distribution of the one you started with. But it doesn't change the shape. So it's important to realize that when I run these values through the z-score formula, it doesn't magically make them normally distributed. The reason that using this normal distribution makes sense is because I knew to start with that the scores are normally distributed. If the scores on the test were, I don't know, exponentially distributed, Pareto distributed, whatever, making them into z-scores doesn't magically allow me to use the normal distribution. You have to know that you're working with a normal distribution. You have to have a normally distributed random variable in the first place, and then when you turn its values into z-scores, it's still normal. If you start with something that's not normally distributed and you use the z-score formula, using this doesn't make any sense. Your probabilities don't make any sense at all. Cool, so keep that in mind. We're going to end up working with a normal distribution all the time in the future when we do statistics for a special reason which we will find out pretty soon. This normal distribution, it comes up a lot, but it doesn't make sense to use a normal distribution, use this Z table, which is using a normal distribution, to evaluate the probabilities of anything that's not known to be normally distributed. Okay,